welcome back, or maybe I should say welcome back to me. I have been a little bit absent the last couple of weeks. Today I have a very, very special guest with me, and that is Mr. Bart Kay. So I wanted to have him on to have a little look at the mechanisms behind how statins are working and what they actually do on a biochemical level. So we'll have a look at what implication that might have in terms of side effects or maybe beneficial effects, and who should be taking these medications and who should not. So over to you, Mr. Kay.
Right. Well, Pim, thank you very much for having me on your fine channel once again. It's a topic which I'm very passionate about and have been very passionate about for a good number of years. It's something that I have been very, very vocal about, and I believe with very, very good reason. So thank you very much for the opportunity to run through the mechanisms a bit for you today.
Oh, thank you.
Thank you. I want to start with a basic sort of very much cursory overview so that people can perhaps grasp some kind of context here, and then we can progressively delve deeper into said rabbit hole as we go along. So in the first instance, the drug class known as the HMG coenzyme A reductase inhibitors, statins in other words, are a drug which blocks the function of a specific enzyme in our metabolic pathway. And the downstream effect of the blockade of that enzyme is that our bodies are less effective at biosynthesizing and creating our own cholesterol. So the first thing we need to do is go and look in a biochemistry textbook, any biochemistry textbook you like that's peer-reviewed, and you will find one and only one form of the molecule cholesterol. It is a high molecular weight alcohol. It is a waxy sort of a substance. It is not a fat. It is a lipid by virtue of not being dissolvable directly in water. And as such, it will not dissolve in the blood plasma and therefore needs to be transported around the body by a class of lipoproteins, as it turns out. And they come in various different forms, ranging from chylomicrons through to very low density lipoproteins. So you have a high density lipoprotein, you have an intermediate density lipoprotein, you have low density lipoproteins, which are split into subcategories as well. Largely the thing that determines what class of transporter molecules we've got is the particular protein that is embedded in the membrane of these transporters, and also the various ratios of lipids to proteins, in other words, the density of these particular things. So these transporters are packets. They are spheroid shape. They're a phospholipid bilayer in which the lipids are contained inside, and the packets float around in the blood because they have their hydrophilic ends pointing outwards, basically. So that's basically how that works. That's how we transport cholesterol around in our body. That said, the first thing that comes to mind when you think about cholesterol is that cholesterol is synthesized in your body by your body under instruction from your genes. Those genes having survived at least 3,800 million years of evolution on this planet. And as it turns out, probably a lot longer than that, having been potentially delivered to this planet from elsewhere via a process that they are proposing is called transpermia, where bits of instructions of DNA and stuff are delivered from planet to planet on rocks that have been floating around in space and things, and then they crash. And anyway, that's for another day. So let's say that life developed in the first instance on this planet. Let's forget transpermia. So there's at least 3,800 million years of evolution that these particular genes have survived. They have been selectively, positively reinforced, while other genes have been wiped out for various different reasons. So there is a reason that our body creates cholesterol. As it turns out, around about 80% of the cholesterol floating around in your blood at any given time was created by your body and not taken in the diet in any way, shape, or form. So cholesterol is, and I'll get to the diagrams that show you this in a minute, but cholesterol is actually made from all the food that you eat, actually. Carbohydrates, fats, proteins, they all can be used to actually biosynthesize cholesterol in your body. So there you go, 80% of the cholesterol in your blood is made by your body under the instructions of your genes. Those genes knowing pretty well what they're doing, actually having been around for a very, very long time doing just that. So
the other 20%, where does that
the other
come from?
20% is thought to be dietary. It's thought to be taken in the diet.
So you're saying that we could potentially change our cholesterol levels with up to 20% by changing our diet?
Well, you would think that that might be a logical progression to make, Pim, but it actually isn't, because the amount of cholesterol in your blood at any given time is set by the action of your genes, and your genes can be turned on and off like a light switch. There are homeostatic mechanisms that say, right now, my body is in state X, Y, or Z. My body finds itself in a particular environment. Therefore, the level of cholesterol I need in my blood right now is X, Y, or Z. If your cholesterol level in your blood is too high, then what happens is there is a transporter that transports that cholesterol out of your blood, back into your bowel, and then you excrete it in the feces. So my cholesterol is too high. Nonsense. You have a transporter that when your body, in its infinite wisdom, decides you have too much cholesterol, will simply crap it out the back end. Okay? If your cholesterol level is too low, because you haven't eaten enough cholesterol, for example, I'm going to reduce my cholesterol by 20% by not eating anything containing cholesterol, then that gene will be upregulated to counteract the change that you are trying to make. Because believe it or not, your body actually knows what it needs better than you do, and much better than any person in a white coat that's had about 10 years of training on such a thing. Your genes have had 3,800 million years of training. That's a lot more than 10. And they're not told what to think by boards of control that sell very, very dangerous drugs for money. So the whole idea that we should interfere at all, actually, in our cholesterol metabolism is completely contraindicated from the ground up. There was never any scientific support for the whole idea anyway. So why are we being told that we need to reduce our cholesterol and cholesterol is bad, etc., etc., etc.? Well, because there were a group of researchers who were looking into the development of atherosclerosis heart disease, and those researchers found an association between a certain subclass, actually, as it turns out, of the lipoproteins and the development of atherosclerosis. So the lipoprotein is, remember, that's the carrier molecule. That's not even cholesterol. And so how they've decided to react to that is, here is an opportunity as a money-making entity, as a drug company, to produce a drug that reduces cholesterol. It doesn't necessarily directly, well, it necessarily does not directly affect the level of the lipoproteins even. There is not one single researcher, medic, or anybody else in the know anywhere in the world who is claiming that cholesterol causes heart disease. The claim is that the various different carriers of cholesterol can be problematic. And as it turns out, this is only remotely true when you take into consideration that said lipoprotein carriers have to be chemically deranged before the body will react to them in such a way as to cause you to develop atherosclerosis heart disease. Now, those chemical derangements come in the form of oxidation and glycation are the two most important ones. So if a particular subclass of your LDL molecules become oxidized, then your body can react to those as if they were an invading pathogen. There can be an immune cascade, and that leads to atherosclerosis heart disease. The same is true if those LDL, that subclass of LDL becomes glycated, meaning it gets damaged by sugar. A native LDL molecule will not be reacted to by your body, cannot cause heart disease. So heart disease is not caused by cholesterol at all. Neither is it caused by native LDL. It is caused by derangements to your LDL. As such, to mitigate, to ameliorate, to prevent heart disease, we need to prevent the oxidation and glycation of our LDL. We don't need to prevent the LDL existing. It exists for a purpose. The purpose it exists for is to deliver cholesterol to the epithelial cells largely. Okay, why do epithelial cells need cholesterol? Well, epithelial cells, like every other cell in your body, have cell membranes around them, which is a phospholipid bilayer. Embedded in that phospholipid bilayer are a bunch of different things, including molecular cholesterol. What is the role of cholesterol there? It is to provide structural integrity for those cells. If you don't have enough cholesterol to maintain the integrity of those cell walls, those cells split open, they break, the contents leak out, those cells basically die. And if your cholesterol level is low enough, you're going to die too, and pretty quickly, actually. So that's kind of the overriding position statement before we get into this class of drugs known as statins, how they've come to pass, what they do, how they work, etc. So are there any questions about that kind of introductory material before we crack on with a few diagrams and bits and bobs?
So if we have cells that are deficient in cholesterol, before the cells are actually breaking, etc., what could happen before that? Because otherwise we would just pretty much die instantly, wouldn't we?
Yeah.
So there must be a progression.
There are a lot of signs and symptoms that your body is deficient in cholesterol, and the various things that will show up depend on exactly what the situation is in your particular body. The example I gave you of the role of cholesterol there in the cell membranes in terms of structural integrity, that's actually just one of literally hundreds and hundreds of different purposes or roles that cholesterol serves in the human body. Okay, and we'll talk about some of those things when we get to some of these diagrams. I think is possibly the best way to go. So let me share with you. Okay, this is a Keg Pathway Diagram, and I would suggest that people really do go and have a look at this Keg Pathway. It's a very interesting little thing to play with. It is interactive. You can do all sorts of things with it. For example, if I mouse over this thing here called up at the top here, can you see my mouse pointer? Yeah, okay. So I'm now circling a molecule called acetyl coenzyme A, which anyone with any knowledge at all on biochemistry will know that is the basic starting point. That is the basic building block of all of our metabolism. When we eat food, be those carbohydrates, proteins, fats, or indeed alcohols actually as well, those things are broken down by our metabolism basically to units of acetyl coenzyme A. Now we can oxidize that acetyl coenzyme A for energy, react it with oxygen, and that produces carbon dioxide plus water, releases energy, and that energy is used to make ATP from ADP plus PI. So that's one of the things we can do with acetyl coenzyme A. It's the first intermediary of the tricarboxylic acid or Krebs cycle, if you like. But also, acetyl coenzyme A is a building block that we can start building other things back up from. Once we've broken our food down into acetyl coenzyme A, we can then use that acetyl coenzyme A to make things. For example, we can use an enzyme called 2, 0.3, 0.1, 0.9 to make acetyl coenzyme A. So let me just show you how this thing works. We can just mouse over this here, and there you see a diagram of acetyl coenzyme A, where the coenzyme A part is parsimoniously just written as CoA there. It's actually a massive, great big molecule to which that other bit is stuck, the functional bit being that tiny little bit, and the and the coenzyme A being this great big thing. We can also mouse over the enzyme there, and we can actually click on that, and it will take us to another page that shows us the chemical reaction. It shows the enzyme. It shows the exact CGT, CD, AGT, the exact genetic code for that enzyme, etc., etc., etc. We can mouse over here, and we get, here's the product of the reaction of 2 acetyl coenzyme A molecules to make an acetyl coenzyme A, which is the first step. Here's another enzyme, and that leads down here, basically either 1 or 2 steps down that metabolic pathway from the very base molecule, the acetyl coenzyme A. We then have a thing called 3-hydroxy-3-methylglutarol coenzyme A. So that's the second most complex, or third if you like, if you count acetyl. That's the second or third most complex thing in our metabolic tree. So it's right at the very base of our metabolic tree, this thing here. So why am I focusing on this thing here? There's what it looks like that. Well, because basically this enzyme here, which in humans is called 1.1.1.34, that one there, that's the enzyme that statins act on. So basically, absolutely everything downstream of that entire pathway, or that entire enzyme there, everything downstream of that is downregulated by the fact that you're taking a statin. What is a statin designed to do? A statin is designed to reduce the level of cholesterol in your blood. In other words, to interfere with what your genes are doing and what they have been doing for 3,800 million years, knowing exactly what they're doing. Here is a little drug that's been invented in the last few years, really, which interferes with that process and basically knocks down the activity of absolutely everything downstream of that point in every branch of the metabolic pathway of the person that's taking that statin.
So,
okay.
Question?
Yes.
How efficient are statins at reducing the enzyme activity? I guess that there is a range depending on what statins you're taking, etc.
There is a range from statin to statin. There is an inter-individual range, absolutely. It seems like you can get 30-35% reductions in your fasted blood cholesterol level. Now remember, this drug acts directly on the molecule cholesterol being produced. This drug has no direct effect whatsoever on any of the lipoprotein carriers, the things that are actually being blamed for the heart disease in the first place. Nobody's blaming cholesterol. They're blaming lipoproteins, and then it's actually only oxidized or glycated ones. This drug does not affect that directly at all. It does have an effect because your body senses that your cholesterol level is lower, so therefore it transcribes, it produces less carrier, because if you've got less cholesterol, then you've got less need for carrier to carry that cholesterol. But that doesn't mean that's a good thing, because you're interfering with what your body is trying to do. For example, let's say you have an inflammatory process going on in your vascular epithelial cells, precisely because you've been eating a pro-inflammatory diet, living a pro-inflammatory lifestyle. Your epithelial cells are upset, there is damage, there is injurious processes that have gone on there. Now, remember what I said about the amount of cholesterol that is in, the role of cholesterol in the integrity of the cell walls, the cell membranes, I should say. It turns out that the amount of cholesterol in every cell membrane equates to about 50%, 1/2 of the weight of everything in that cell membrane. Cholesterol is vastly, vastly important to cell membranes. If you have damaged cells that are trying to repair themselves, they're going to want a lot of cholesterol delivered, which means your cholesterol level is going to be high in your blood because your body will be making it from acetyl coenzyme A precisely to repair the damage that's being done. And also your body will be producing transporters to get it there so that it can do that job repairing. So you take a statin and you are interfering with your body's natural healing process. You are knocking down its ability to do precisely what it absolutely should do. But it doesn't end there in terms of the problem, because, well, let's find cholesterol, shall we, on this chart. So up here, this is where the statin works, right up here, yeah? So 1 step, 2 steps, 3 steps, a 4th step, a 5th step. Not even on this page. We have to go to another page. Then we need to go to steroid biosynthesis.
Which is the next tab.
Which is the next tab. This one here. Thank you for that. Okay, and then there's all these steps here. Steppity, steppity, steps, steppity, step, step, steps, all this kind of stuff. There's cholesterol at the bottom of the second page. Many, many steps below where that drug acts. And there's a whole bunch of stuff that is sidelined to that, if we go back to our first tab here, that is deleteriously or negatively affected by knocking down this enzyme all the way up here. So let me give you some examples of it. Over here, we have a bunch of different things which are collectively referred to as the prenalated proteins. They are vital in the correct folding of proteins for enzymes, among other things. Your cell cannot function well or optimally if you cannot fold proteins the right way to make enzymes the right shape to catalyze the right reactions. So that's going to have a whole bunch of negative effects on cell function, a whole bunch of completely unpredictable effects in each individual person, depending on the balance of this, that, and the other thing. But that is definitely not a good thing. If you knock down prenalated proteins enough, you can actually kill a cell stone dead. And in fact, that is one of the areas where cancer researchers are looking to find specific prenalated proteins that they can knock out in cancer cells to kill those cancer cells off, for example. But if you have a healthy, functioning, normal cell and you knock down the prenalated proteins in that cell, then you knock down that cell's function and you cause that cell to become distressed. And cell distress is not a good thing in terms of how that how that pans out in terms of overall body function. So that's a serious side effect that you can potentially expose yourself to if you are foolhardy enough to take these dangerous toxins known as statins. Okay, so that's that one there. Down here, we've got the steroid synthesis. That's where you've got the knockdown of the actual cholesterol molecule itself. And we can deal with some of the issues of knocking down cholesterol itself in a minute. But in the meantime, let's look at some of these side chain issues as well. So we've got the prenalated proteins. Down here, we've got the N-glycan biosynthesis down at the bottom left-hand here. N-glycans do a lot of different roles in cells as well, but probably their primary role is in the function of your immunoglobulins. So if you take a statin and you knock down your ability, therefore, to produce immunoglobulins that function properly, then you may well be affecting your ability to mount an effective defense against infection. So that can't possibly be a good thing either. Okay. Over here, down at the bottom right, we've got ubiquinone and other terpenoid quinone biosynthesis here. That's where you make all your respiratory chain coenzymes, like, for example, ubiquinone, coenzyme Q10. In other words, this is why we say, those of us that know how this thing works, that statins are a dangerous mitochondrial poison. They knock down your ability to produce coenzyme Q10. Coenzyme Q10 is vital in the respiratory chain, in the electron transport chain. Without that, it knocks down your ability to produce energy, to undertake antioxidant activity. It can cause rhabdomyolysis in high energy cells like muscle cells. In other words, that can cause muscle cells to die, to break down, to split open, to cause all sorts of issues going on with those. Now, statins are supposed to protect your heart, and your heart is a muscle. So actually, here's a drug that supposedly is protecting your heart from a disease, when actually it's, if anything, it's likely to increase your risk of having heart disease. And at the very least, many people who take statins experience muscle pain, stiffness, things that feel like fibromyalgia, that kind of stuff. And it's because this drug is basically tearing down their ability to produce energy in those muscle cells. Very, very bad, very, very dangerous. You can cause irreversible damage to skeletal muscles, smooth muscles, and indeed cardiac muscles by taking statin drugs. Not good at all. What else have we got on here? We've also got an inability...
Just a question, if that's okay.
Please, absolutely, yes.
So whenever they prescribe statins, as far as I know, they usually recommend that you take Q10 with that as a supplement. Yep. How efficient is that in preventing any sort of mitochondrial damage or damage to the ability of making energy?
Unknown. Well, it's unknown, and I'll tell you why. Because as far as I'm aware to date, and I did do a quick search this morning, a cursory search, I was not able to identify any literature where they have identified a transporter anywhere in the human digestive system that can absorb whole coenzyme Q10 as ingested. What happens when you ingest coenzyme Q10? Your body goes, oh, there's a protein, I'm going to split it down into its amino acids. Those amino acids will then be absorbed into my blood, and then my body will use those amino acids to make whatever proteins that it sees fit based on its normal metabolic function. Whoops, it's unable to make coenzyme Q10 because the statin knocks it down. I doubt very much that supplementing with coenzyme Q10 would be remotely effective in ameliorating the very serious risks of damage to your skeletal muscle and indeed your cardiac muscle from taking statins. So that's the answer to that one, as I understand it.
Cool.
If others know more about that than myself and have seen that there are transporters, then please do let us know underneath this video so that I can update my knowledge on that. But as it stands, that seems to be what the situation is there. What else have we got on here? Under the ubiquinones here, the coenzyme, the Q10, all that kind of stuff, all the Qs, not just 10, but all of them actually, 10 being the most important, I suppose. Also down here, that knocks down your ability to produce vitamin K and other clotting cofactors and clotting complement, basically. So, you know, that's another potential problem. Not necessarily a good thing. A lot of the physicians are saying, well, that's great because it means you're less likely to have blood clots, et cetera, et cetera, et cetera. To which, of course, we say, well, instead of knocking down your ability to produce blood clots, why don't we deal with the thing that's causing the disease process in the first place, which is chronic systemic inflammation and not cholesterol in the blood? Anyway, that would be way too logical, I guess, and perhaps not remotely as effective at generating income for companies that produce statin medications and thereby provide physicians with kickbacks and things for prescribing lots and lots of jolly good statins to people. So those are kind of some of the side chain issues there. If we now go back to the next tab again, where we came up with, well, here's cholesterol all the way down here. What we now can also see is that our ability to produce bile acid is dependent on our level of cholesterol, because bile acid is synthesized directly from cholesterol. So if you take a statin, you are now going to be less likely to be able to metabolically deal with fat in your diet. You're more likely to suffer all sorts of secondary problems around that, including your inability to absorb and use any of the fat-soluble nutrients and vitamins and things that you need. Well, there's going to be a problem potentially. You are unable to break down excess steroid in your system as well. So you're now going to have a potential regulation issue there. You're not going to be able to produce enough steroid hormones. And what am I talking about? Well, the most important ones there are estrogen for women and testosterone for men. So that's going to subject you, if you're a woman, to a higher likelihood of osteopenia, osteoporosis, fractures, and secondary problems associated with that, up to and including death. Because actually one of the largest causes of death in aged women are blood clots, which are a direct result of fractures of the hip of femur, pretty much, which is also made more likely in older age, both in men and in women, by the fact that you have a less ability for your brain to function properly, for your vestibular function to function properly, to actually be able to sense where your head is in relation to the rest of your body and the gravitational field. You're more likely to fall over. And you're more likely to fall over if your neurons are not working properly. For neurons to work properly, they require effective insulation. The insulation that neurons use is called myelin. They're called myelin sheaths. And myelin is biosynthesized directly from, you guessed it, cholesterol. So the statin will knock down your ability to myelinate and use your neurons effectively. Added to that as well, there is a very, very serious and invariably fatal neurodegenerative disease known as ALS, which there has been at least one epidoodly-moodly gemology study done on where they had a statin population and a non-statin population who were match-paired reasonably well otherwise. And the risk ratio differential between statin takers and non-statin takers for ALS or Lou Gehrig's disease, if you take a statin, your risk of that invariably fatal neurodegenerative disease goes up. But not even a little bit. It goes up by 16,700%. Gosh, I wonder why. Maybe it's to do with the direct effect that statins have on neuron degeneration and myelin sheathing and all that kind of stuff.
Do you know how many percent of statin takers are actually suffering from ALS, though?
It's a very small number. However, when you want to talk about relative risk ratios instead of absolute, 16,700 is impressive. That's enough to have a look at and go, the incidence goes up here markedly. So while ever the absolute incidence is very low, as you quite rightly point out there, Pim, it is still massively, massively higher in that population. So the number of people who take statins that get ALS is probably very low. But the number of people who don't take statins and get ALS is massively lower than that. And given that ALS is invariably fatal, I think that's a serious concern. And we'll get rid of this chart in a minute so that we can chat a bit more, but you've also got all sorts of other effects when you lower your cholesterol production around things like you can't produce enough vitamin D2. Obviously, it affects your ability to make vitamin D3 because that comes directly, both of those come directly from cholesterol as well. And vitamin D3 is the most important cofactor for all the other enzyme functions throughout your entire metabolic pathway. So basically what we have here in terms of statins is we have a dangerous, contraindicated, metabolic and direct mitochondrial toxin which knocks down your ability to produce cholesterol, the thing that your body has designed a process to do over 3,800 million years. Nobody is even suggesting that cholesterol is causing a problem in the first place. They're suggesting it's the transporters. This drug does not act on the transporters. It acts on the cholesterol, thus reducing the production of transporters. The effect that statins have, when you look at the epidemiology that's been done, you will find that populations of individuals who take statins enjoy a statistically significant, but in absolute terms, very, very small reduction in the reoccurrence of heart disease following an initial event. Okay, so what I'm saying is, well, let's break down the epidemiology as it exists accurately so that people know what it says. Basically, it says if you are a man and you are over 65 years of age and you have already had a heart attack, then statins are associated with a lower second heart attack rate. Very, very small amount, not even a huge effect. Okay, if you are a woman of any age, that data does not apply to you. There is no evidence in support of reducing cholesterol having any effect on heart disease in females. None. Okay, if you are a man who is under 65 years of age, that data does not apply to you either. There is no evidence in support of it for under 65-year-olds. If you have not already had a heart attack, then it does not apply to you either. This only applies if you have already had a heart attack and you're a male and you're over 65. That is the only epidemiology that actually supports any meaningful effect on heart disease outcomes in any patient group. Okay. That being said, why does that happen? Well, it happens because one of the side chain things that also comes out from that first chart in the prenalated proteins area is that it knocks down one of the inflammatory pathways, which is highly involved in the chronic systemic inflammation around heart disease development. So what we're saying is the drug actually works on inflammation. It's an anti-inflammatory. And the drug designers never had that intention in mind. It's just a serendipitous thing that has happened by the virtue that they've knocked out an enzyme so high up on the tree that while it has all this negative effects over here, there's this one tiny little positive thing around inflammation. Okay, so why not just take an anti-inflammatory that doesn't have all this negative side effect stuff and achieve the same thing? One wonders. Well, it's because they still want to say cholesterol is the problem, and it never was. They still want to say that native lipoproteins are the problem, and they never were. They still are ignoring the fact that the problem is oxidation and glycation of the transporters, not the fact that the transporters exist. They still want to push that barrier because it's still profitable, massively profitable. I think in the US alone, I think statin medications are profitable to the tune of billions of US dollars a year. And so these drug companies are not going to let go of this one easily. They're going to keep telling physicians that LDL is the problem and keep coming up with pseudoscientific, ridiculous, associative, nonsensical garbage to support that completely unsupportable argument. And they're going to jealously guard that source of income for as long as they possibly can manage to do so. So that's basically the story on the statin medications, how they work, etc. As a final point, let me say this. While statins have been shown to have that positive effect on second heart attacks in men only over 65, what you'll find in any population that you look at large is that the difference in all-cause mortality is actually the inverse of that. So let me just share with you something else here. Okay, so the line here that's important, the data set that's important for this bit of the discussion is the dark blue, which is the highest data set. It's this data set here on this chart. On the vertical axis here, the y-axis, we have the all-cause mortality, age-adjusted, per 100,000 persons per year. These dots here are different countries. So we have, I think it's 130-something different countries here. What we have here is tens and probably hundreds of millions of person years of data. And so we have high mortality up here and low mortality down here. On the x-axis, the horizontal axis, we have low blood cholesterol at the left, and we have high blood cholesterol at the right. We have a strong positive correlation here that says the higher your fasting blood cholesterol, the less likely you are to die for any reason. End of discussion. Done. We're finished here. So there you have it.
Well, on that diagram, it obviously starts going up again.
Yeah, at the end, there's a little hookup at the end at the very highest levels of blood cholesterol. I have looked at the data, and it looks very much like that is an artifact of there being a much lower number of data points in that range of the data set. We can look at it again if you like, and I'll show it to you again. Mm-hmm. It's a very good point, and it's a point well made. I'm glad that you actually did ask that question. Okay, so there it is there. So what you'll see is there's quite a bit of data here in this sort of straight line part of the graph. Over here, there are very, very few data points. And so the hooking up there from the line of best fit, you could actually still fit a straight line through that data set, like so, and it probably wouldn't affect your R-squared value particularly very much. It just so happens that these researchers that have put this chart together have fitted the least squares regression that they possibly could find. So they've used an exponential or a curved relationship or regression line here. However, what I'm suggesting is a straight line could just as well be drawn through that data set, because look, there's 1, 2, 3, 4, 5. There's only 5 data points there, 6 if you count Germany down there, above 220 in terms of the blood cholesterol. So we really need a lot more data there to actually get a true indication of it, I would say. What we can definitely say is that the lowest, or the nadir on that line, if we were to use that curve line there, would suggest to you that the safest blood cholesterol level to maintain and to keep is about 225, which is significantly higher than any medical professional will tell you should have. Yeah?
Yep.
Happy with that?
Yep.
Cool bananas. Okay, so questions?
Yes, so you were saying that when we're blocking this pathway or partially blocking it or whatever we're doing, obviously the amount of cholesterol that we are able to produce goes down, but it doesn't affect LDL. Even so, when you go in and you take a blood test, your LDL will go down if you're taking statins. Do you want to explain why that is?
Yeah, basically the gene that encodes for the construction of an LDL, a transporter for cholesterol, if there is a lot of cholesterol in your blood, your body senses that and turns that gene on, like a light switch, on. Makes some transporter to transport all this cholesterol to where it needs to go. If you lower the amount of cholesterol in your blood, that switch gets turned off. I don't need transporter to transport something that isn't there. So when I said it doesn't affect the lipoproteins directly, that's what I mean. It does affect them. If you knock down cholesterol production, you knock down also the production of the transporter for the cholesterol by a knock-on effect, because your body senses that.
Cool. And what about if it might not be as common, but sometimes HDL goes up? So what's that about then? Why would that go up?
Okay, so the different lipoprotein classes, you have your HDLs, you have your IDLs, you have your LDLs, you have your VLDLs, you have your remnants, you have your chylomicrons at the other end. Sure, okay. Each one of those transporters has a specific job. It's by its very structure, its very shape, the exact protein that's embedded in its membrane, it will lock and key bind to different tissue types. It does different things. Okay, so HDL is a transporter that is largely concerned with collecting up cholesterol and taking it back to the liver. So if the level of cholesterol in your blood gets to a point where it's no longer useful, then the gene that makes HDL is switched on and it starts ramping that up so that it can clear the cholesterol out, allowing more space in the blood for other things that the blood needs to do. For example, that's why HDL is often referred to as good cholesterol. Absolutely ridiculous nomenclature, because the cholesterol that's carried by an HDL is exactly the same. It is molecularly identical to the cholesterol carried by LDL, for example. It's just a different protein, phospholipid protein, actually, that that carries cholesterol around, and it's involved in scavenging, cleaning up, picking up cholesterol and taking it back to the liver for processing there. So again, there are different switches, there are different precipitants that turn the switches on and off for those genes. Basically what I'm saying is your genes are a concerted package of different links of DNA that encode for the production of different transporters when we're talking about the transport of cholesterol. And each one of them has individual on-off switches depending on what's going on. And as I say, your genes have been doing this for 3,800 million years at least. They know what they're doing. They do it right. The only people who have a problem really with cholesterol, and it's not even really a problem with cholesterol, to be clear about it, these are people who are actually about a 1 in 1 million of the population. They have either a partial or a complete knockout of the gene that encodes for the transporter that allows the cholesterol to go across the cell membranes in the epithelial cells. In other words, these are people who, regardless of transporters, regardless of level of cholesterol, they cannot get the cholesterol out of their blood and into their cells. So those people generally are identified medically very soon after birth because they become symptomatic very, very quickly of a problem. Usually those people don't make it to teenage. They die very, very young. And it's not because they don't die because they have very high cholesterol in their blood. They die because their cells are absolutely starved of cholesterol, which is a very, very different thing. So those people have a problem. They have an irreversible genetic problem, as I say, that usually takes those people out before they reach reproductive age. So that's as it is. Then there are another group of people who are called people with familial hypercholesterolemia, which means their particular genes, the way their particular genes work, means that they tend to have a higher fasting blood cholesterol level than is normal. And they are therefore determined by the medical profession to be abnormal, and their presentation is called hyper. Those people are no more likely to develop heart disease than the general population. There is no experimental work to support that posit anywhere existing in the literature. And when you look at the epidemiology, again, the incidence rates are so close to zero in terms of the difference as makes no odds to any given individual over a 100-year lifespan. It's just nonsense. There you go. Statins, dangerous, contraindicated, metabolic, and mitochondrial poison that knocks down cholesterol. Cholesterol doesn't even cause heart disease. No one's saying that it does. Having knocked down your cholesterol, there's a whole bunch of negative side effects in doing that. However, we get to a lowering of the LDL level, which wasn't causing the heart disease either. And is there any evidence that that's efficacious? Well, no, because when you look at the epidemiology around blood cholesterol, because when you have a blood cholesterol test, you go to the doctor and you get your blood cholesterol tested, they're not testing cholesterol. They just call it a cholesterol test. They are testing the concentrations of the lipoprotein carriers. That's why they give you cholesterol broken down as LDL, HDL, etc., etc., etc. They're not even testing your cholesterol level. The whole thing is completely ridiculous. I hope that covers it.
We'll cover that later, I think.
Yes.
It's going to take too long to do that now.
Yep.
So pretty much what we can say, even if you are male, you've had a previous heart attack or whatever, you are over 65 years of age, taking a statin will only help you in one aspect, maybe to reduce your risk for another heart attack, but your overall mortality will go up.
Correctly, because it will actually cause you to be more likely to get other fatal side effects. And so it balances out at least to zero, and more likely, in fact, the taking of a statin will kill you sooner than you would have died otherwise.
So, in effect, statins are probably no good for anyone.
I'd go further than that. I would say statins are absolutely, fundamentally, completely contraindicated for all people at all times. Nobody should ever touch that drug with a 10-foot barge pole.
Right. What about
Simple
a
as that.
12-foot one?
Well, that's even more betterer. Keep statins away from your body.
Yeah.
Basically.
So if someone is on a statin now, they see this and they're getting quite worried about it, how should they go about getting off of those statins? Do we have time to talk about that briefly?
Sure. Okay. Statins are not one of those drugs that will cause you a problem if you just drop it immediately. There is no wean off period. There are no side effects that you're going to get from getting rid of that statin and getting rid of it yesterday. So that's the first thing I would suggest. Do not touch another statin as long as you live, however long that is. Do not take advice from anyone who tells you that a statin is a good idea. They are ignorant. They do not know what they are talking about. They are not supported by science. Epidemiology is not science. There is no experimental science to support the use of statins in existence anywhere in the literature, and that person is not competent to advise you on your health. I would get rid of them as well from my life straight away if that was at all possible. The next thing I would do is I would look into everything you can possibly do to reduce your chronic inflammation status in your life. That means you should be electrically earthing for as much of the time as is feasible, possible for you to achieve. There are videos about that on my fine YouTube channel if you'd like to go and have a look for those. I would also suggest to you that you eat a diet which is maximally anti-inflammatory, and that is a diet that does not contain any plant material whatsoever, by the way. Boys and girls, stay away from all plant sources of so-called nutrition. They are all inflammatory to some degree or another. I would suggest to you that you might want to consider anti-inflammatory type nutraceuticals, one of which I'm involved in marketing, which you will see an interview about later this week on my fine channel, actually. That will be coming up. What else is there around anti-inflammatory? I would get your psychological distress in order as much as you possibly can. I would get plenty of direct sunlight. I would get plenty of exercise at an appropriate level for your age and stage, whatever that is. That would be my approach to all of those kind of things.
And sleep.
Yeah, good point. Sleep.
Sleep is good.
Sleep is very good.
Okay, so where can people find this fine channel of yours?
Okay, well, if you do a Google on Bart Kay, you can't not find me. Basically, I'll be the first 2 pages of listings that come up on any Google search or any kind of search really of my name. My channel is called Bart Kay Nutrition Science Watchdog, as you can see up in the corner of the screen up there. Yeah, can't miss me. That's where to find me. There's an amount of stuff that is you can just watch there for free, and I suggest that you do so, including there are more than 35 different videos, many hours of science-based information and education regarding cholesterol and heart disease and cardiovascular pathophysiology, which is what I used to be a lecturer in before I retired, by the way, in case you didn't know that. I'd go and look at that stuff. But also, if you want to be a member of my channel, you can do that by clicking the join button, which is beside the subscribe button on the front page of my channel. And there are various different levels that you can subscribe to my channel to there, where you will get access to other videos that you can't see for free. And also, I have a Patreon channel, which is just patreon.com/Bart_K. And there's also a subscribe star there as well, which is a parallel offering. And they are the places that it is best to find me.
Awesome. Right. Thank you so much for going through all of that. I hope that has shed a little bit of light on why statins might not be so good for you. A lot of the time I find that people are very hesitant going off of the medications, they're scared. But when you actually look at the mechanisms,
Yeah.
you will see that it's not actually, there is no reason for you to be scared. You have processes in your body that are supposed to be there for a reason.
And people believe their doctors. People are trained to believe their doctors from a very young age. People deify doctors, actually. You need to understand that your doctor is just a person and not a deity. They are a person who has undergone 10 or so years of education specifically. And when I say education, the process of becoming a physician is actually not an education, it's an indoctrination. They are taught paint by numbers to react to certain situations in a given way. They are not allowed to think for themselves. They are not allowed to try this or that or the other thing. They have a very clear mandated course of action. If you present with a blood cholesterol level above this level X, then they are required to write you a prescription for statins and lean on you hard and tell you to take them.
Yep.
They are not allowed to do anything different from that. If they do, they will be struck off. They will lose their livelihood. Okay? A scientist like myself, especially one who is now a retired scientist, is able to tell you the truth and is able to speak to you about what the science actually says. I would be a bit more careful about where you get your advice from if I were you, frankly.
Yep. Just keep in mind that what we're telling you is not medical advice, because we're
Correct.
not actually qualified to do so, but we want to encourage you to do your own research and look at the mechanisms of what's actually going on in your body.
Yep. Good point. Well made.
Yep.
It's not medical advice. And frankly, I wouldn't want to give medical advice, because if I was giving medical advice, I'd be giving advice based on what someone told me to say. And I wouldn't be allowed to think about it or apply any science in any way, shape or form, just like what doctors do.
There you go. So thank you very much for watching, and I will see you again next week.
See ya.
Bye.